Hi, this is Alfawzia Nihar from At Home Tuition. Welcome to our session today. The topic that we are going to discuss in our today's video is Riemann sum. In this video, we are going to discuss a detailed information regarding the Riemann sum as definite integral. We can approximate the area under the curve sin x square by breaking that figure up into pieces whose areas can be well approximated by trapezoids. So this can focus on formalizing that idea. Our goal in this video is to define Riemann sums and the definite integral and to do some computation with these. So in what follows, we will be adding together long list of numbers. So we begin by introducing a convenient shorthand for this. For instance, we will write, do you see this notation? Summation of j is equal to 0 to 3j. This is just to represent the sum of 0, 1, 2 and 3. 0 plus 1 plus 2 plus 3. That can be written in the shorthand form of this. We refer to this as summation notation. The E-like symbol is a command to sum what follows. The j equal to 0 below the summation tells us to start at 0 and the 3 above the summation tells us to stop when we get to 3. Thus, j runs from 0 to 3. The j on the inside of the summation tells us to add each of the numbers. J is equal to 0, j equal to 1, j equal to 2, j equal to 3. As an another example, let me write. Please look at this expression. We can also write this sum in the first notation that I have shown you. 4 plus 9 plus 16, 25, 36, 49. Please look at all these numbers. These are perfect squares. So these numbers can be written as 4 can be written as 2 square, 9 as 3 square, 16 as 4 square, 25 as 5 square, same way 6 square and 7 square. So we are adding together the squares starting from the second square to 7th. Therefore, this can be written in the summation notation. Does this make sense to you? J starts from 2 and ends at 7 and this expression is written as the squares, sum of the squares. This is not the only representation of our sum in this notation. For instance, you can also rewrite the same thing. You can try this by plugging in all the numbers. If you start from 1, 1 plus 1 square, I mean 2 square, 2 plus 1 the square, that is 3 square. Can you follow so far? I am writing the same thing in the different notation. The expression is different. Notation is same, summation notation, but the expression is different. One same thing can be written in different ways. So it is all about you. You can pick the one that is very comfortable for you and that makes more sense to you. Please notice that summation notation is just a notation. It allows us to write long sums in a very compact notation. It does not provide us with a method for quickly finding the sum. It is just a way to quickly write down a sum. We can now define Riemann sums and definite integrals. Suppose the function f of x is defined on an interval, closed interval a comma b, and let n be a positive integer. Now we can define delta x. Delta x is nothing but b minus a over n. Now let me define x0, x1, x2 and till xn. You can take any variable. x0 be a, x1 be a plus delta x, x2 be a plus 2 delta x. And you can define in the same way. And let j be the last number, xj be a plus j delta x, where j is any integer from 0 to n. I may occasionally refer to the points xj as the partition points. Please notice that xn is nothing but, in the place of delta x, I am just replacing the formula b minus a over n. N gets cancelled out. And a plus b minus a also gets cancelled out. So xn will be just b. Now let us define the nth right hand sum of f of x on the interval a comma b. This is the right hand sum. This can be simply written as summation of j is equal to 1 to n f of xj delta x. Hope you are clear with this. In the same way, we can also write the nth left-hand sum of the function f of x on the same interval, closed interval a comma b. For the right sum I use R, and for the left sum I'm going to use L. For the left sum we will be starting from x0 and end just before xn. I mean we will be stopping at x suffix n minus 1 itself, and this also can be written as in the summation notation. Hope you're clear with this one. Ln and Rn are both referred to as Riemann sums. Actually, Riemann sums refers to a much larger class of expressions, of which both Rn and Ln are special cases. We will not look into this more general Riemann sums in this video. For most functions, including all bounded continuous functions, the left and the right hand sum approaches a common value as n tends to infinity. So limit n tends to infinity. When n approaches infinity, both left hand sum and right hand sum of the Riemann will be equal. The definite integral of the function f of x on the interval a comma b, it can be denoted by integral over a to b f of x dx, and this is the common value, and this can be written as limit n tends to infinity ln, which is equal to limit n tends to infinity Rn. So after the next few examples we will get a better idea of what all of this means. For now I just want to point out that the definite integral a to b f of x dx and the indefinite integral, these are two totally different types of objects. The indefinite integral is the family of all antiderivatives of f of x. Thus, integral f of x dx is a family of functions. The definite integral is just a number. However, a little later we will see that these two integrals are actually very close related. The definite integral is defined as the limit of approximating sums. There is always the possibility that the approximating sums do not have a limit. Thus, we say that a function is integrable, provided that limits defining the definite integral exist. We won't worry about this condition too much, since nearly every function we will run into that will be integrable. Bounded continuous functions are always integrable. And let's talk about even functions also. Even functions with a finite number of jumps or holes are always continuous. Please notice that by just looking at the graph, when there is a jump or hole, we think that this is a discontinuous one. But even functions with a finite number of jumps and holes are always continuous. We can find functions with infinitely many jumps which are integrable, while non-integrable functions do exist, and we have to look really hard to find them. That is very rare. Let us also talk about the error bound for increasing functions. If f of x, the function, is increasing on the interval a comma b, then for all n, ln, the left hand sum is less than or equal to the integral a to b f of x dx less than or equal to the right hand sum. So this can be written as, I can just subtract ln from both these sides. I'll just show you in the furthermore method. I'm just using the Riemann sum definition here, and integral over f of x dx minus ln. If I'm just subtracting ln, this can be written as f of b minus f of a, the definition, times delta x. Delta x is nothing but b minus a over n. So this is the error bound for increasing functions. We can also define error bound for decreasing functions in the same way. For that one we will be taking the right hand sum. So the same function f of x and on the same interval a comma b. So this is how it will be defined. If f of x is a decreasing function on a comma b is a closed interval, then for all n, Rn, it should be Rn and Ln. Rn, the right hand sum, is less than or equal to the integral a to b f of x dx less than or equal to ln. Furthermore, you can just rewrite this as ln minus. So this can be written as ln minus integral less than or equal to f of a minus f of b times delta x, which is nothing but b minus a over n. And when you compare this with the error bound for the increasing function, there are a lot of ideas in what we just did. So you will probably need to work through a couple of examples, some few examples, and before all of these ideas sink in. So there we had f of b minus f of a, here f of a minus f of b. That makes a lot of difference between these two. Hope you're clear with the introduction and the concept that we discussed for Riemann sum and the definite integral. In case if you get any query, you can let me know. In our upcoming video, we can discuss the example for the Riemann sum problems and also for the error bound for both increasing as well as decreasing functions. See you in the next video. Have a good